Hi friends, let's continue our discussion on torsional loading. Or torsion. So in the last video, this is a shaft. If it is subjected to the equal and opposite couple about the longitudinal axis, then it is called the twisting moment. Or if some shaft like this, if it is subjected to equal and opposite couple about the transverse axis like this, then this is nothing but the bending moment. And we have also seen that if some shaft like this is subjected to some twisting moment like this, and this is a shaft of maybe, and we have seen that at some section xx at point x, somewhere at x distance from the point A, we have seen that if we make the cut section xx and if we take that particular element x, then we have seen that due to the action of this twisting moment T, there will be some internal resisting force that will be generated within the members cross section, which is parallel or tangential to the cross section. Tangential internal resisting force at cross section. So this tangential internal resisting force per unit area is called the shear stress. This shear stress is generally denoted as tau, and also dealt with the twisting moment at a particular section, the sign convention and all those things. So let's discuss about the distribution of shear stress. Distribution of shear stress. For that case, let's consider some shaft like this, that this NBA fixed end for some frame of reference purpose. Our shaft is having some length L. This will be the center of the cross section O, and this is having some radius R. Let's consider a line on shaft like this, and let this shaft is subjected to some twisting moment like this. Okay, so upon the application of this twisting moment, what happens is that this point gets displaced to this particular point, but here this point will not be changing. So let's name this as A and this as B, and let this be B dash. So this will get displaced to its new position. If we take a line to the center of the cross section like this, then the cross section will have made theta angle between these two points. Okay, so this is what happens when a shaft which is fastened at the one side, and if we provide the twisting moment on the other side, the cross section at the end section, which is free to rotate, will be rotating with respect to the sense of the twisting moment. Here we can see that at the cross section the displacement is proportional to R. Like if this is a cross section, and if we consider this is the point B, and let this as the point B dash, this is the center of P, then we can see that as the radius is increased, the displacement of the points that we are considering is maximum. So displacement is proportional to radius R, therefore resistance is also proportional to R. So this resistance is nothing but shear stress tau, that is proportional to R. Let's replace this proportionality constant by a term K into radius R. So we can see that the shear stress is varying linearly with radius r. So shear stress is having linear variation at any cross section of the shaft under consideration. So if we take equilibrium of moment or for a particular case of shaft like this, which is subjected to twisting moment, and if we take this section and if we consider this particular section AX over here and like this, then we are having some shear forces over here. Then if we take the equilibrium of moments, we can write, let this be T is equal to tau into dA, which is the shear force acting on the differential area dA, into this constitute the force, and into the r, which is nothing but the radius r, which will constitute the moment. For the entire cross section, just integrate to give the net value of moment. So this is the equilibrium moment. Then we can rewrite this as T is equal to integral K into R into dA into R. So we can rewrite this equation as K can be taken out of this particular integral. Since it is a constant, we can write K into integral R square dA. So in the left hand side there is twisting moment T, and we know that this term integral R square dA is nothing but the polar moment of inertia of cross section. So we can write T is equal to K into J, and from this we can write K is equal to T by J. Let this be the equation number 2, and let this be equation number 1. If we substitute 2 in 1, which will leads tau is equal to Kr, which is tau is equal to T by J into R. We can rewrite this as tau by R is equal to T by J. So that's it. That's about the equilibrium of moments, and we will be getting this particular equation. This very important equation. From this equation, we can write tau is equal to T by J into R. So the maximum value of shear stress, that is tau max, which is very important in the design point of view, tau max will be is equal to T by J into R max. So this equation can be used to determine the tau max, which is the maximum shear stress. And if we are having this equation, then if we are provided with some solid shaft, then we can write tau max is equal to, then this be having diameter d, tau max is equal to T by J into R max. We know that J is equal to pi d raised to 4 by 32, and R max is equal to d by 2. So substituting these terms, we can write tau max is equal to T by pi d raised to 4 into d by 2 into 32. And from this equation, we can write 16T by pi d cube as tau max for solid shafts. And if we are provided with some hollow shaft, then we know that tau max is equal to T by J into R max. Let's suppose this is the hollow shaft, and we are provided with, this is DI and this is DO. Then we can write tau max is equal to T by J into R max, where J is equal to pi do raised to 4 minus dA raised to 4 by 32, and R max is dO by 2. So in these terms we can write T by pi dO raised to 4 into R max dO by 2 into dA raised to 4 into dO by 2 into 32, which will giving, which is 16T dO by pi dO raised to 4 minus dA raised to 4. If we do some manipulations, we can write 16T into dO by pi into dO raised to 4 into 1 minus dA by dO raised to 4. And if we cancel these two terms, then we can write tau max is equal to 16T by pi dO cube into 1 minus dA by dO the whole raised to 4. And if we rewrite dA by dO by a constant beta, then this will give you an equation tau max is equal to 16T by pi dO cube into 1 minus beta raised to 4. So this can be used for the equation of shear stress, maximum shear stress for the hollow shaft. So that's about the maximum shear stress terms. So similar to the Hooke's law in axial loading, we are having Hooke's law in shear. So let this be the shaft. This is having some length L. This is having radius O, and this is the center of this cross section O, and these lines are separated by the angle theta, and due to the twisting moment T, let this angle be gamma. So let this be the shaft subjected to twisting moment at the end section, and A, the end of the shaft is fixed, B is the section at the free end, and due to the twisting moment T, at the point B moves to the B dash, and the cross section dimensions and the theta, it is the angle that is between the deformed and undeformed line AB, and AB dash is gamma. Let's write the Hooke's law. Hooke's law simply means stress proportional to strain. Here we are having shear stress tau. Shear strain is given by gamma. So we can rewrite this as by changing the proportionality by applying proportionality constant, which is equal to G into gamma, where G is modulus of rigidity, which is a material property. Modulus of rigidity, gamma is the shear strain, and tau is the shear stress. So this is the Hooke's law in shear. Let's elaborate this by writing tau is equal to G into, instead of gamma we can write this gamma is equal to this BB dash from the figure, BB dash by L. L gamma is equal to BB dash. From this, gamma is equal to BB dash by L. Similarly, from the figure at this section we can see that BB dash is equal to R theta. So we can write G into R theta by L is equal to tau. So from this equation we can also write as tau by R is equal to G into theta by L. So this tau by r is also given by an equation. In the previous cases, tau by r is equal to t by j. So we can rewrite this entire equation as t by j is equal to tau by r is equal to g theta by L. And this is the universal equation of torsional loading. So that's it.